So, Mr. Burke, a couple of students came up to me and asked me for some help on shapes of molecules. So I was wondering if we could do that. Give them a lesson on how to come up with the shapes of these molecules.
Back to good old geometry.
Yeah, exactly. That's good.
Right.
So, so how do we go about it? You know, if we have this nice center atom here, and what we're going to do is we're just going to try to come up with different numbers of bonds that come from this.
Okay.
Okay.
That works.
So this will be our center atom, right?
Okay.
Okay. So I think we're going to let you do the honors of taking this. And what we're going to do is we're going to just start off with something really simple. So the simplest atom would be those that have the lowest number of bonds.
Right.
Okay. So how about if we start off with 2?
Works for me.
Okay.
And of course, we do want them as far away from each other as possible, right?
That's good. That's a good point. Why is that, though?
Well, electrons don't like each other.
That's true. They're both negative, right?
Positively.
So they are as far apart as possible. What angle would that be?
Well, it's half a circle, and a circle is 360, so it'd be 180, right?
Be 180, right? Exactly. And we have an example of that. Here's our example. This is beryllium dihydride, I do believe. And so it's an actual model of that linear shape. And those are 180 degrees apart from each other. So good, you did a good job.
Thank you.
It looks just like it. Okay, so we're going to go on. Let's try a third bond. And you're free to change that any way you want to.
Okay, because if I put a third one in now, I wouldn't get max separation, right?
Right. So if we put in like this, I think we can do better than that, right?
I think you're right.
Okay.
So let's see if we can do it. Which one's what? How about that?
Well, that's pretty good. So if you look at it, it looks like you've taken up all this 360 degree circle.
Right.
So what would those angles be?
Well, 120 equals 360 divided by 3, right?
That's true. Right.
So 120, 120, 120.
That's pretty much as far apart as they can be.
I think so.
Okay. So we do also have an example of that in our library here. So this is boron trichloride. And lo and behold, it's exactly like that.
It does look like that, doesn't it?
So it seems like actual molecules actually look like our little ball and stick figures.
That works.
That's neat. Okay, so we're going to go ahead and take a look at a fourth bond.
Okay.
So we're going to try one more and see what you can do with that.
All right. Well, I have a feeling that if we keep it in the same plane, all right. Let's get this a little crooked. Pretty close.
Yeah. So that is the same plane, and they're pretty much as far apart as they can be. If you're looking at kind of a two-dimensional thing, that'd be 90 degrees apart from each other, right?
90 apart.
And so if you take 360 divided by 4,
90
that's
degrees.
90 degrees.
All right angles.
Exactly. The problem is this. This isn't a circle. It's a sphere.
That's right.
So do you think they can get farther apart than 90 degrees?
How about?
This is arguably the hardest one to build.
Yeah. And I was ahead of myself, that's why.
Okay, it's sort of like a landing craft.
Yeah, like Sputnik.
Exactly. So we have this, they look like they're beyond 90 degrees. So, so what do you think they are?
Well, maybe about, since that's 90 to here, like 110, 100, something like that.
Okay, I'm about
Close.
110 degrees. Good. I think the published degrees is 109.5, but that's pretty darn close. So let's see. Let's see what our model has for us. So
Okay.
this is carbon tetrachloride, and it's just like our model
It
here.
is. It looks really
I think our
close.
model is shedding some skin there, but
Some quarks.
exactly. Okay, so can we go on? I mean, I imagine there's some sort of limit where you can't fit any more bonds around an atom,
Mm-hmm.
but I think we can probably go another time,
Yeah,
maybe two.
maybe.
So,
Do we want to kind of name this? Because
oh yeah, that's true.
should we name it?
We should name it.
All right.
Okay.
So, as we look at it, it's not in the same plane. But funny thing is, I can start to see triangles.
We do, and if you look at it, the sides, you have 3 triangles, then you have one on the bottom,
Right?
that's 4 triangles.
Yep.
So 4 is tetra,
Right? Just like tetrachloride.
right? So
Tetrahedral
tetrahedral.
works for me.
This would be tetrahedral. We'll go back and name those other ones too.
Those
but-
are easier.
Yeah, those are easier. This is a tetrahedral. So if you forget that, 4 bonds means tetra, just like the game Tetris.
Right.
With 4 blocks.
Exactly.
Okay, so let's try this other one.
All right. You're going to be difficult on this one, all right? All right. Let's go back to... I can't remember which one I'm doing. No, good.
It isn't as easy as it looks.
No, don't try this at home. Try it in the lab the next time you're here. I still got one more. Where am I going to put that?
Right at the bottom.
How about that?
Now that's pretty symmetrical. That's
Yeah.
a nice shape.
I like that.
So you have 3 around the center, right?
Yeah.
So that's that trigonal shape that we had
Right.
before. And then you have one out and one back.
Right.
That's good. So if I'm looking at this correctly, it looks like we have 120 degrees around the
Right? 120 on these 3.
right, and then we have 90 going up and down.
Going up and
Good.
down.
That's nice.
Yeah.
So that's pretty much as far apart as we can make them. Okay. So we'll go to the picture and then we'll try to figure out how to name that thing.
That works.
So here is a picture of phosphorus tetrachloride.
Okay.
Oh, I'm sorry, pentachloride,
It's
because we have 5.
Right.
So so let's go with the same strategy we did with the tetrahedral.
Okay.
Okay, so do we have
Well,
some sort of side things that we can look at?
we've got triangles, right, in one plane, and we've got triangles in another.
Oh, yeah, we have two sets of triangles.
Right.
And they sort of make, if you look at it, it sort of makes a pyramid.
That's right. So, how about trigonal bipyramidal?
Trigonal bipyramidal, that's a perfect name for this one. Okay, trigonal bipyramidal. You know, we are reaching the maximum of our bonds,
Right.
but I think our atom can fit one more. So, let's fit one more.
Okay. And it's not going to be up my nose. How about...
That seemed like a nice, easy conversion there.
It was, because in the one plane, I just had to change that 120 to 90. So I've got all right angles all the way around.
So all 90 degrees and 180 degrees across from each
Yep.
other. So that's good. That's pretty much as far apart as they can go.
I think so.
So
On the
we'll
same
get
atom.
we'll get our model up here, and let's see what here is sulfur hexafluoride. So 6 bonds to that. So, what do you think? What do you think about this one? You know, we do have lots of sides on it, right?
Right. And kind of like when we were looking at the tetrahedron, and we had 4 sides, we now have 8.
8 sides. Oh, 8 octa?
Octo.
So
How about
octahedron?
Octahedral.
That's great. So, quick review. Octahedron,
Right.
right?
Don't ask me to
Octahedron.
redo them, though.
That's right. No. We have a trigonal bipyramidal.
Trigonal bipyramidal.
Okay. We have a tetrahedral. We have a,
Trigonal planar,
Trigonal
because they're
planar.
all in the same plane.
exactly, good. And we have, last but not least,
Linear.
is linear. Good. I think that's going to help a lot.
I think you're right.
Okay. Thank you,
Good.
Ms. Burke.
Thank you, sir.